So now we have basically evaluated an equation where the amplitude x equals p divided by k times cos omega t minus 5 divided by square root of 1 minus r square whole thing squared plus 2 beta r whole thing squared. Right, so where this r is the frequency ratio, omega divided by omega n, right? So where this omega is the angular speed of the vibration, right? Omega n is the natural frequency, right? So now by using this equation, now there is a question. Now let's consider what is the question. So that means in this question it says a machine component of mass, while reading we will take the data. Machine component of mass 4 kilograms. Okay, so that means mass of the machine is 4 kilograms. Vibrates in a viscous medium. Okay, fine. Harmonic excitation force. Right, harmonic excitation force. That means here we have the mass, right? On this mass there is a kind of a harmonic excitation force that is acting. So let's call it P cos omega t, right? So now here we have the spring. Let's say this is the ground. Okay. So what is the value of that harmonic excitation force? 40 Newton. Okay. P equals 40 Newton. Okay, right. And also because of this harmonic excitation force, right, it causes a resonant amplitude. Of course, because of the vibrations there is a kind of an amplitude, but here what it actually causes is the resonant amplitude. That means the maximum amplitude. So what is the value of that amplitude? X. So that x equals 30 millimeters, right? So as according to the basics, you know, at resonance omega equals omega n. That means the frequency of vibration equals to the natural frequency at the resonance. Okay. Periodic time t, that is also given. What is the periodic time? 0.31 seconds. Okay. Now this is the resonance scenario. That means definitely omega equals omega n. That means omega divided by omega n equals 1. That means r equals 1. So now when considering this equation, you have to worry about the modulus of the amplitude, right? That means you don't have to worry about this cosine part because it is the modulus. So amplitude modulus equals P divided by K divided by square root 1 minus r squared whole thing squared plus 2 beta r whole thing squared. And also you know now our r equals 1. So that means x modulus equals P divided by K square root 2 beta r. That means r is 1. That means 2 beta whole thing squared. Right? So now x is the modulus. That is always positive. So that means square root of 2 beta squared is 2 beta. Right? That means P divided by K divided by 2 beta. Divided by 2 beta. Okay? Right. So now what is the target? We have to find the damping coefficient, right? So that is what they are asking. We have to find C. What is the damping coefficient of this vibration, right? How can we find that? Because we know this beta is the damping ratio. Beta is the damping ratio, right? And also beta equals C by C naught, right? What is C? Damping coefficient, right? What is C naught? That is the critical damping coefficient, or in other words, the critical damping constant. C naught is the critical value. C is the value that we have to find. The C is the damping constant and the C naught is the critical damping constant. And how can we find C naught? Okay, first let's evaluate what is beta, right? So P divided by K2, that means this we can say P divided by 2 beta K, right? P divided by 2 beta K. That means beta equals P divided by 2 amplitude and K. Okay, right. So now I will again erase this part. Beta equals, what is P? P is the force, that is 40 newtons. Okay. 2, okay, multiplied by what is X? X is the amplitude, 13 millimeters. 13 millimeters, you have to keep the standard units, right? That means 13 you have to divide by 1000, right? That means 0.013, right? And K, stiffness. How can you find K? Right, okay, fine. So now the next target is to find K. Okay, I will just put a box like this, right? Right. So now we know omega, angular speed, equals 2 pi f. That means angular speed equals 2 pi times angular frequency, right? And also it equals 2 pi times what is frequency? That is the reciprocal of the periodic time, 2 pi divided by t, right? So you know the periodic time. What is the periodic time? I think you have mentioned there, 0.31 seconds. 2 pi divided by 0.31, right? And also this is the resonance scenario. That means this also equals to omega n, right? And also we know that where should I write it? Okay, I will write it here. Also we know that K divided by M equals omega n squared. K divided by M equals omega n squared. That means what is K? K equals omega n squared times M. M, you know, that is the mass of this system, right? So now here the missing part is K. Now you know what is K. That is omega n squared times the mass. What is the mass? 4 kilograms, right? So in the calculator, 40 divided by 2 multiplied by 0.013 multiplied by what is omega n squared. Omega, you know, 2 pi divided by 0.31. 2 pi divided by 0.31. 0.31 whole thing squared times 4. So that is beta. Let's find that. 40 divided by 2 0.013 then frequency 4. Okay, 2 pi divided by 0.31. 0.936. So my answer for the damping ratio is 0.936. 0.936. 0.936 is the damping ratio. Okay. Now I will again erase. Right. So now what is the damping constant or the damping coefficient? Beta equals C by C naught. And C naught is the critical damping constant, and there is a separate equation for the critical damping constant, that is C divided by C naught equals twice m times omega n, twice mass of the system times the natural frequency, right? That's very easy now. We could have originally substituted this equation over there, right? But doesn't matter. It's okay. So now we have to find C. So what is C? You can subject C. C equals 2m omega n times beta. Beta you have already evaluated, right? So 2 multiplied by mass is 4. Natural frequency is 2 pi divided by 0.31. Damping ratio is 0.936. Let's calculate. The answer will be 151.77. The damping coefficient or the damping constant is 151.77. What are the units? Newton seconds per meter, right? So that's it. Again check the calculations, right? So in case if I have gone wrong, please let me know, right? So that is the way to do that. Thank you.
Okay, right. So now there is a mistake in the original diagram that I have sketched in the video where I was explaining the calculation, right? So here in this diagram you can clearly see I have marked the force P cos omega t, which is the excitation force, and we have the mass. Then here I have marked only the spring, right? But now this mass is actually connected through a viscous medium, right, in addition to the spring, because that is already explained in the problem, right? Because in the problem it is said that this mass is vibrating in a viscous medium under the excitation force P cos omega t. So now what you have to do is you have to sketch a damper also, right? So let me sketch the damper like this. Okay, right. So now that's it. That means it is something similar to this, right? The mass is there, then the spring, and then the damper, right? The motion of the system you can consider along any direction. Okay, let's say the motion of the system is x active